Welcome, everyone. I think it's time we start. Hello. So I wanted to welcome everyone for coming at the 42nd Johns Hopkins workshop, which is starting today and will be for the entire week. As you may know, this is a series of workshops that it's taking place in different places, and last year was in Budapest. This year is in Florence. This is part of a GGI workshop that we've been running for 6 weeks, and this is the 7th week. Our title, and the title of this week, is Beyond the Standard Model, where do we go from here? We do not expect to get an answer during this week necessarily, but we hope there is going to be more, thinking about this question, and maybe we will see what happens in the future from what starts this week and in the last 6. Yes, if you want to connect, you can use, as usual, EduRoam. If it doesn't work, as it happens, for instance, for me, you can try this other one. You just have to click, and it's going to be, it lets you online. So it's a pleasure to introduce the first speaker, David Kaplan from Johns Hopkins University, who's going to tell us Beyond the Standard Model.
Test. Okay. Too loud? Okay. Good morning. So, you know, sometimes you go to a conference and you forget how long your talk was supposed to be, and you write it not remembering it, and then you discover it's much shorter than you're supposed to. So there will be parts of this talk that we fly through at high speed, and you should think of those parts of the talk as advertisements for talks that if you would like to hear about, I'm happy to give it in my office or in the coffee or something like that. Or you can just go to sleep during that period. So I'm supposed to talk about Beyond the Standard Model, and this will be, of course, very idiosyncratic. This is my opinion. I hope I don't upset too many people too long, but maybe be prepared to be a little upset. Okay. The Standard Model and whatever comes next, Beyond the Standard Model. How can we very generally talk about Beyond the Standard Model? Well, there could be new physics at higher energies. That means new states, new particles, or schmutz, whatever an unparticle is, or something that doesn't look like resonances. Or it could be suppressed operators. Your collider doesn't quite reach it, but there's new physics. It has subtle effects. Higher dimensional operators is a way of parameterizing the unknown. Then there's weak couplings, and for most of my life as a physicist, this was sort of the second tier interest, and that's evolving now in time, as the first hasn't borne a lot of fruit. This is also new states. They just happen to be light and very weakly coupled, or perhaps the light states are turned on in the background. Maybe there's sources of something that lives back there in new interactions. Or you can go really violently and say, I want to violate general relativity. Of course, anytime you violate general relativity, there is always some formulation in terms of new fields or new states. So in a sense, that lives back in the weak couplings. Or you say, I want to violate Lorentz invariance. Of course, if you add general relativity to something that violates Lorentz invariance, you undoubtedly get, again, new states. Or you can violate quantum mechanics. None of us have really figured out a nice way to parameterize violations of quantum mechanics, and when you do, you can imagine all hell breaks loose. So really, a lot of work in thinking generally parameterized beyond the standard model has still led to the same types of physics. I'm going to write down the B minus L gauge boson. I apologize for those who have seen this slide or set. B minus L gauge boson is just some okay type of new physics. It's a new gauge boson. It can fit into grand unified theories. It is nice for anomaly reasons. So you can ask, here's something that we look for, and how do we look for it? Here's an old plot from Atlas, which should be updated in my slides. And this plot is a constraint on a new gauge boson, somewhere between hundreds of GeV and 3.5 TeV. It's a direct search looking for a peak, looking for a bump in the data. Now, of course, the indirect searches have been done, in fact, before the LHC. Bounds on compositeness or new contact interactions at LEP also suppresses the exchange of at that point, something we couldn't reach. But of course, we're being very restrictive because B minus L is a nice symmetry. It could be a nice symmetry anywhere. We should be able to look very low energies. And so at low energies, you start to look at lower energy colliders, even Babar B factories and neutrino experiments. There are different ways to see it all the way down to a GeV. You're still looking for a resonance. Now, you can keep going down, and as you get really light, 1 GeV, 1 MeV, 1 keV, 1 EV, then you have to start worrying about astrophysics. You can worry about whether it's captured in the sun. Fixed target experiments in the high end become important, but lower than that, supernova, sun cooling, globular clusters, other astrophysical objects put severe constraints on these type of objects. And then the coupling is required to be much less. If you keep going, then you get a long-range force. You have something which can extend from here to the moon or to the galactic center, and for that force then gives you an EP, or equivalence principle violating force, that you can put constraints on. And the coupling must be much weaker than the gravitational coupling. B minus L in this range is interesting because B minus L doesn't decay in this shaded region, so of course it could be dark matter. And so that's another reason why this might be interesting. So I like this example because it's something that covers all bases. I've always tried to find the plot that shows you can go to high energies, you can go to weak coupling. Here's one particle of new physics that covers the whole thing. But instead of just randomly picking out nice models, or just random objects you can add to the standard model, we're guided often by hints or discrepancies or annoyances in the standard model. The numbers on the right are the number of orders of magnitude that the problem upsets us. Let's say it's the cosmological constant problem, the hierarchy problem, strong CP problem, patterns in fermion masses. Also, not tuning, but the source of matter antimatter. Why is there more matter than antimatter? And the source of inflation. Inflation is, in a sense, a solution, but it has its own problems. And then, often not talked about like a problem, but something that's there, something interesting, or sometimes even an afterthought, is dark matter. Let's talk about the hierarchy problem. Let me apologize. Okay. Supersymmetry. Look, so I emailed Roberto and I said, is my title of my talk a placeholder, or do I really have to summarize its current status beyond standard model? He said, no, it's a placeholder. Talk about whatever you want. I said, I want to talk about the cosmological constant. He said, great, but maybe you should also talk about whether the gluino at a couple TeV is still counts, means that we're fine-tuned for supersymmetry. Should we keep pushing stop limits, etc.? Okay. To be honest, in 2006, I saw this plot which parameterizes the MSSM, the constrained MSSM, or the minimal supersymmetric model. And the green, at that time, that green band was the allowed parameter space. So rescaling of the masses by the mu term showed the inherent fine-tuning in this parameter space. And I thought, my God, I should make a movie about what's going on here. And sometimes we react violently to these sorts of things. So I love this plot. I showed it every talk for a year. And the plot looks much worse now, as you can imagine. I don't have the resolution on this computer. So you can argue, well, yeah, but that's the minimal, blah, blah, blah. We can move things around. It looks better if you split the thing or you make things degenerate or da-da-da-da-da. Okay, yes, it's true. That's true. I don't know how to parameterize that tuning. How do we know that your theory with 7 extra pieces and the spectrum that you have some vague argument why it looks like that, why is that not considered tuning? I don't know how to, even this tuning is sort of perfunctory. The original model of supersymmetry had tuning in the sense that, model tuning, theory tuning, in the sense that if you ask just from higher dimensional operators, what should the squarks, what their mass should be compared to the gluino mass? Should they be of order of magnitude? And if you write down some operators, you can make yourself believe, yes, it's very natural for them to be the same. The mass of the gluino and the mass of the squarks is the same. But we made a model tuning in there quietly. In the hidden sector, the x's could be any object in the hidden sector, the object that has the biggest supersymmetry breaking VEV. Whereas the singlet, it has to be an absolute singlet to live in that operator. So that's a special thing. You need a singlet that gets roughly the maximum F term, and in addition, has no instabilities. So that was already model tuning, but once we accepted that, then supersymmetry looked great, except we had a mu problem, and then, see? Generically, if you didn't do that, generically, the scalar masses should be a factor of a loop factor, 16 pi squared greater than the gaugino masses should be. Could be more. The gaugino masses, and those who discovered anomaly mediation, does have a contribution, and if M is M Planck, this can be saturated. But it's still a big hierarchy, and this is where the Higgs lives. And so your job, the exercise, is figure out what experiment should have discovered the gluino, in what year. I'm not going to tell you the answer, but that's your exercise. At the end of the week, when I'm chairing the last session, I want to hear the answer. When should we have discovered the gluino and said, yes, supersymmetry is natural? Okay. That's supersymmetry. But generally, what we talk about for the last couple of decades is what can make the Higgs mass natural, and that is by just making the standard model incorrect at the mass of the Higgs, or near there. And so one of the hard things was that the LHC is so good and has done such an excellent job at ruling out new colored states that you could imagine other clever ways of generating the hierarchy without new colored states, but states that carry, say, Electroweak quantum numbers, or even, and I don't mean to be hyperbolic, but even just something that comes through the Higgs portal. So all that is saying is that we should keep searching. Bounds on, in the parameterization of supersymmetry, bounds on charginos and neutralinos are quite low compared to stops and gluinos. So, of course, we should keep searching, and our bias shouldn't be that those should be naturally light. That's an artifact of supersymmetry. I took this plot, this chart from Nathaniel Craig's talk in Paris back in, I think it was May or June when I was there. It's a great talk. It has 21 ways to solve the hierarchy problem, from boring to completely insane. Let me tell you the one that's right in the middle. The Relaxion. Now, why am I bringing up the Relaxion? Yes, okay, I wrote a paper called the Relaxion. The name was derided by my co-authors. That was my main contribution to the work, in fact, is the title. The idea of the Relaxion generally, generically, is the statement that perhaps you can solve the hierarchy problem without putting new states at the weak scale. That the standard model could be mostly correct below the Higgs mass or well above the Higgs mass. Mostly up, except for a single particle or field, which is a very light state. And in the simplest model, where we simply add a coupling of it both to the Higgs and to QCD. That coupling to QCD looks like an axion coupling. And the axion coupling at low energies, once QCD confines, Here is the two-flavor model that I took from Villadoro et al. This is the potential. It's some periodic potential with a period f, and the coefficient of the axion potential is proportional to the pion mass squared. The neutral pion mass is mostly roughly linearly proportional to the Higgs VeV, which means the axion potential is sensitive to what the value of the Higgs mass is, or the Higgs expectation value. And that was the key. If the axion, or that phi field, can change in time very slowly, it could potentially stop when the Higgs is the value we want. It naturally triggers it through this coupling. And so this rough linear dependence of the axion periodic potential means that in some places, the values of the Higgs, there could be no barriers or negligible, and in other parts it could be large, and parameters can be such that very close to the transition between, say, positive renormalized mass squared, negative renormalized mass squared, somewhere in there, the barriers become important compared to the slope. And then you get stuck. And then you wait a long time, and it's today, and we ask why the Higgs is fine-tuned. The three biggest complaints about the Relaxion is that in the original model, the one that actually is nice, not the uglier one, is the strong CP problem is messed up. Another complaint, problem, issue is that the field evolution of phi is extremely long. If you really want to get some mileage out of this model, phi needs to roll much longer than a Planck scale. And third, it strains the multiverse CC solution. We've added many vacua, and that's going to change the dynamics of how we solve the cosmological constant problem using a landscape. Let me address those problems. The Relaxion strong CP problem is the fact that I've used the axion potential to stop the rolling versus a slope. So it is exactly the axion plus a slope, which is an order 1 strength compared to the barriers. That means you've displaced theta QCD from its nice minimum at 0 to something like, as soon as the barriers just start to turn on, an order 1 number. And order 1 is bad. It's ruled out by 10 orders of magnitude, and that's the problem. And so question is there a fix? Here's a fix that I can't get myself to write up, so here it is. This is the write-up. And if it makes sense to you, then you can cite this and just keep using it, or write it yourself and ignore this talk if you want. You can use the axion, but you just stop the evolution earlier, meaning don't get the Higgs VeV to be 100 GeV, get the Higgs VeV to be 10 eV, 10 orders of magnitude too small. Now, why is that useful? You put in a slope, you get stuck at a value where the Electroweak scale is way too tiny. You've oversolved the hierarchy problem. And in fact, to do it, you find that the Higgs mass has to be roughly 200 GeV squared in the positive. And because of QCD breaking of the Electroweak symmetry, this generates a VeV, which is of order 10 eV. And the point is that it's very easy to de-fine-tune the Higgs. We've now fine-tuned the Higgs to some small mass, a positive, roughly weak scale. And what you can imagine is that sometime later, after this fixing of the tiny Electroweak scale, some other field rolls. It's the inflaton or a waterfall field or a curvaton. Something rolls. It has a tiny CP even coupling to the standard model. Since everything's connected by loops, it evolves the Higgs. And so the fine-tuning of the Higgs gets messed up such that you can get back an Electroweak scale VeV, but now the barriers are huge compared to the slope, and that ratio, that theta parameter, is now roughly 10 to the minus 10. It's interesting because if you want to go less than 10 to the minus 10, you need a positive Higgs mass greater than 200 GeV, And so in order to get the right electroweak scale, you actually have to reintroduce some fine-tuning. If the positive Higgs mass was 1,000 TeV and you needed it to be negative 100 GeV squared, that would require tuning. So 10 to the minus 10 is actually roughly the limit where this mechanism works, which is a prediction then that we should see neutron electric dipole moments very soon. Another complaint is the field extent of phi, and I hear that this is a very terrible thing, to be much longer than M Planck, and there are reasons why it could be terrible. There are statements in string theory and suggestions and parts of string theory where things can be calculated, that if you move more than M Planck, you're guaranteed to bring down an enormous number of states. Things get really bad. It may have conflicts with the weak gravity conjecture. All of this, to an extent, assumes that the theory is good all the way up to the Planck scale. You can construct low energy theories or medium energy theories like clockwork that allow you to create field extents. They may have other sicknesses associated with string theory or quantum gravity, so if there's a very rigorous statement that absolutely it's not allowed, fantastic. But if it solves a problem, in fact, what are we doing? We're saying there's a big hierarchy in the standard model, the Higgs mass on a very high scale. We are translating that hierarchy into essentially a long evolution of a field. If it's rigorously ruled out, that would be very interesting. If this is the solution, it would have interesting implications for the theory of quantum gravity. There are ways to avoid it. There are interesting, better versions of the Relaxion in a sense. There's a so-called thermal Relaxion. Actually, I don't know if it's called that, but I think it should be called that, where the friction of the rolling field that's tuning the Higgs mass is due to not Hubble, but by the fact that phi, that rolling, that condensate, can decay into electroweak physics. And thus, you imagine a field that's rolling very fast over barriers, and when the electroweak gauge bosons are light enough, it can dump its energy and get stuck behind a barrier, thus picking out the electroweak scale, not having to roll very far. Phi doesn't actually have to be very light. And it's an interesting version of this story. The third complaint about the Relaxion is that if you have the Relaxion, it means you have all of these new minima, and the problem with all these new minima is I've solved the cosmological constant problem using anthropics and a multiverse. And that means all these other minima could be places that you could solve the cosmological constant problem and not the hierarchy problem. And so the complaint would be that while you're in de Sitter space, you could have rare but possible transitions into these later vacua and potentially have eternal inflation because you're trying to solve the cosmological constant problem. So there appears to be tension between the Relaxion solution of the hierarchy problem and the cosmological constant problem. So the obvious thing to do is to try to solve the cosmological constant problem in a way that does not invoke the multiverse and anthropics and landscapes and things like that. In fact, the rolling solution to the hierarchy problem would suggest that the solution to the cosmological constant problem that would fit the best is also some evolving cosmological constant in the early universe. You can imagine solving the hierarchy problem first, getting the Higgs mass stuck, and then evolving the cosmological constant and letting it get stuck at some tiny value, if you can do it. Now this part goes even faster, I apologize. But like I said, we can talk over there. Relaxing the cosmological constant. We want to try the dynamical relaxation, first tried by Abbott and Tom Banks in the mid-80s. Abbott had a nice explicit model. The model had a couple of problems. It spit out an empty universe, and it spit out, and it predicted eternal inflation, which gives it the measure problem and the landscape type of arguments that we're trying to avoid. We, at this point, believe we have an existence proof of a simple solution, and this is assuming that the universe can bounce. And that I will not give a talk about, but it's in that paper. Also controversial, maybe crap, I think maybe not. Here's the basic idea. It's a very simple experiment you can do during the coffee break, is just draw a potential, just a slope. Phi has some linear potential, it can roll. Start it rolling at some cosmological constant, lambda 1 to the fourth, and if its distance from the place it crosses 0 is much larger than m Planck, then as it rolls, it slowly rolls until it hits m Planck, and then it rolls fast, and it rolls fast past until it gets to a negative cosmological constant. Now, parametrically, first, we have a limit on the upper cosmological constant. I want to require that there's no eternal inflation, which is that quantum fluctuations are smaller than the classical rolling. That puts a limit on how shallow the slope can be. Fast roll begins as soon as you hit m Planck. As soon as you're within an m Planck, this is similar to inflation. If you're less than m Planck away for a single field, you get fast roll, and that determines what lambda 2 is. And so together, there's a bound. Lambda 1 has to be less than this geometric combination of lambda 2 and m Planck. If you set lambda 2 to the cosmological constant today, you find lambda 1 can be as big as 10 capital MeV. Well, so what? The field is rolling, it's rolling very fast, it could keep rolling. How does that help? The point is that when it gets down here, the universe is filled with the kinetic energy of the roll and the vacuum energy. The vacuum energy is negative, the kinetic energy is positive. You can show that in a finite time, in order distance m Planck, you start to contract. The universe starts to get smaller. And the universe is kinetic energy dominated. And so it goes as 1 over a cubed, phi dot, or phi dot squared is 1 over a to the 6th. And you can calculate, as it contracts, how far phi rolls during that whole time. As it contracts, the Hubble scale goes way up. So the time scale gets shorter and shorter. And so, amazingly, another exercise, the change in phi is only m Planck times a log ratio of the scale factor you start with to the scale factor you end up with during contraction. Which means it parametrically doesn't go very far, or parametrically only logarithmically farther, which means this negative cosmological constant is still small compared to the positive cosmological constant. If you couple it to a gauge sector, all the kinetic energy from the rolling can go into heating that sector. So this is worked out even relatively recently by people who actually work on thermal field theory, and you find that there's a friction associated with rolling when you're coupled to light gauge bosons through the axion-like coupling. And that allows, once the universe is contracting, that allows all that kinetic energy to be dumped into heat. And so if you have some mass threshold where all of a sudden you can start to dump the rolling into a thermal bath, and you have some constraints on that F parameter, then you can reheat the universe. You've contracted, instead of a coherent rolling field, you have now a thermal bath. You need to start the runaway of dumping energy, so there are subtleties. This is a form of friction where gauge bosons become unstable. This is also in the thermal version of the Relaxion. So you can show, these are details that I'm going too fast, so I'm not going to do it. Ta-da-da. That's it. It heats up. The rolling heats up. Phi doesn't roll too far. You have a contracting universe. We make an assumption. We make an assumption that you bounce. So how does that fit into the observed cosmology? You've tuned the cosmological constant to a tiny negative value. You're contracting. You've heated up the universe. Now its density is much higher than milli-eV. And the long period that comes before is actually a period of inflation. So it's quite flat. The only problem was that you ended that period of inflation at milli-eV energy densities or less, which is far too low to start things like Big Bang nucleosynthesis. So we need to contract, we need to bounce to get the universe heading in the right direction, and that energy density, the thermal stuff, starts the universe. You can ask, does this mess up the homogeneity and the flatness that we got in the earlier case? And the real question is, do we need to add more inflation to get the perturbation spectrum? It turns out, preliminarily, no. You can get a nice perturbation spectrum. Here's the history of the universe. You expand, you get very cold, you're CC dominated, the CC is tuning, you get a small negative cosmological constant, and you contract, you're negative, you're kinetic energy dominated, you dump the kinetic energy into radiation, your radiation dominated during the contraction. The miracle occurs, there's a bounce, and then you start to expand, and you have normal Big Bang cosmology. And phi, which has been rolling, has not rolled very far, and parametrically, the cosmological constant is small. Here are things I don't have time to talk about. Standard cosmology is a period of inflation, and the normal Big Bang cosmology, perturbations leave and re-enter the horizon, and they're flat because Hubble is constant roughly during inflation. This is what our cosmology looks like. Period of inflation, contraction, we're going backwards in A, we come back, and now, and amazingly, it turns out that you can get a set of perturbations which are scale invariant and left the horizon when the universe was actually much bigger and colder than it is today. And the contraction period actually enhances the perturbations. There are ugly parts. We need to make the we have a tiny negative CC, we want a positive CC. That's ugly. It only goes up to 10 capital MeV, so you need higher stages. We show you can get higher stages. It appears we can go all the way to M Planck with the CC. Working out. Are there observables? Yeah, if something is rolling today, there's a dark energy equation of state, which is not -1. We're looking for it. People are looking for it. More interesting is if you have couplings to a photon of a rolling field today, then that coupling to a photon produces a birefringence in all the polarizations in the CMB. That means E modes turn into B modes. We're looking for that. Even if the coupling to the photon is suppressed by M Planck, this produces a difference from W equals -1 by 1%. These probes will be much more sensitive to that rolling field. It may even be possible to do dark energy in the lab. There's a nice ring which is being used for doing measurements of proton EDMs, or should be in the future. And we have found that there are also effects from a rolling dark energy field. If this coupling to the photon exists, that should be able to put constraints of the coupling to the photon greater than 10 to the 9 GeV. This is with Yanis Semmerzides. My statement about all these problems, I call them problems, but these are just problems of small parameters. We get uncomfortable with tuning. We call them problems as if it's inconsistent. It's of course not. We can just make the numbers small. Antimatter, matter, inflation, these are just initial conditions. There's nothing wrong with the theory. They're hints that maybe something is new. Dark matter is the only thing that's wrong with the standard model. The standard model is wrong because there's other types of matter. It's dark matter. That's what this talk should have been about. Sorry. There's a range of dark matter you can do with lots of interesting experiments. That's from Catherine Zurich's talk this summer. This is from Peter Graham's talk this summer. This is Surjit Rajendran's talk this summer. You should have invited somebody else, to give this talk. Macho searches. Dark matter could be anywhere from many times the solar mass to 10 to the minus 12 22 electron volts. It's the real anomaly in the standard model. There are lots of things to do. There are going to be lots of talks in this conference. My favorite of these is Surjit Rajendra's talk at Paris in June. That link will be here. Of course, there are anomalies. Those could already be hints that there's something going on. But many solutions. So in our mind, as we talk about the LHC, which is obviously very important, it has destroyed the life of many people. There are also a lot of solutions, a lot of interesting physics with light particles. And that's it. Thank you.
We have time for questions. You can raise your hands if you want. So maybe I can ask you why I was surprised you didn't mention any gravitational waves from these strange bounces. Is there anything, or
we're working on it? Yeah, we're working on it. Yeah, that would be great. That would be great. Yeah.
Okay.
Yeah, but I don't know.
Can you say a little bit about this experimental signature of dark energy that you are considering with Yannis?
Yeah, we just started this, and this idea was 2 weeks ago. And we sent an email thinking it would never work. But they're doing EDM measurement, so they're looking for a precession of this magic frequency. So they've lined up they've lined up the spin in such a way that it precesses exactly once as it goes around the beam. And then they look for precessions out of the plane, and that will be an EDM measurement. In the same way, you're coupled to an axion, so this is like your axion wind experiment, basically. So here, because you have a beam, if you just have dark energy, you have no gradients. So zero gradients will be zero effect. But since you have a beam, you're boosted with respect to the background. And so in the boosted frame, the rolling axion has a gradient. And now we gain a little bit because dark matter, in the case of dark matter, it's 10 to the minus 3 C. Here it's 1 because it's 0.7 GeV is the beam energy. And so you can gain from that for a high energy beam. There are a lot of systematics that we're not sure that they'll be able to erase. The stability of the beam, actually knowing the path of the beam, making sure that the electric field is exactly in the plane, and to what extent it's not, all those things will provide contributions to rotation of the polarization. So we don't know, but it's sort of squiggly level. It looks like you can get 10 to the 9 GeV.
So it's just very interesting to see. It's Casper Electric, not Casper Wind, and it's very interesting to see whether there's a
Casper Electric. Which one? Yeah, it's the fermion coupling.
Yeah, it's the EDM coupling is Casper Electric.
Yeah. Okay, so it's Casper Electric.
Yeah, so it's very interesting to see if there is a signature there.
For Casper Electric, yeah. No, we should. But of course, this was in the office with Peter. So Peter should have thought of Casper Electric. So I don't know why he thought we hadn't thought about but the difference here for dark energy is that you need velocity. So Casper Electric is only moving as fast as the Earth is moving. So you get a gain because the beam is relativistic. And so that's my guess is what it is. Versus the background, we're moving 10 to the minus 3 in the galaxy. Here we're moving 1. So
I think we are ready to move on. Thank you, David.
Can you hear me well? Sì. Sì. Vai per te.
Ok. Okay, so now we move to experimental talks, and next one is Lorenzo Bianchini from Pisa, who's going to tell us about the Higgs and the Electroweak sector results and perspectives.
Okay, yes, thanks. No, I think it doesn't work. Okay, I can use the keys. It doesn't matter. Okay, yes. So it's my pleasure to give you an overview of the experimental results. Okay, definitely cannot be a complete talk. Okay, I will just give you some highlights, especially from this last summer. We had a lot of them. First, to put the thing in the correct context, we are at the end of round 2 of the LHC. Okay, so we are approaching the second long shutdown. The round 2 gave us order 30 to 40 inverse femtobarn per experiment over 3 years. Okay, starting 2016, actually 2015, but the bulk came the year after. So most of the analysis, so the 2016 data have been really deeply scrutinized. So almost a complete set of results from this data set, improved the search and measurements compared to round 1, new observation. 2017, only a few results are available up to now, especially those that were sensitive to, they could have allowed us to make observations, essentially, okay? And we'll give you, I will show you which one later. And then, if you include the full data, 3 years, so we reach 113 inverse femtobarn, but at the moment there are not yet results available, okay? And I would say that we have to wait at least 1 year between the end of one run and when the first results appear. So sometimes late next year we will have the full update. Plus a special run. Okay, there's been a low pile-up run, small integrated luminosity, 200 inverse picobarn. You can see it here. Okay, this peak in the average number of simultaneous proton-proton interaction per bunch crossing. So the average is pretty large, it's 37. Okay, you remember that the 30 was the baseline when the LHC design, and now we are taking data at twice the luminosity, the design luminosity. The small run as a special physics was requested for a special case, that is the measurement of the W boson transverse momentum through the recoil method. Okay, essentially this one. Plus, I guess when you have a low pile-up, you can afford to lower the thresholds when you may have access to phase space that usually you cannot access. And the results are expected to appear soon. Now, electroweak physics. Z and W are really bright candles, okay, at LHC. With the current beam condition, you expect 40 Hertz per lepton pair and 400 Hertz per single lepton, okay? So it's really a huge data sample. So LEP has been overseeded by far in terms of number of Z collected, and W's same story. Here the story is a bit different with respect to the other results, because most of what is presented here, also in these references, are run 1 data analysis. The reason being that most of these analyses require either very clean data samples, so low pile-up, for example, and then it's something that we could have in run 1, 7 or 8 TV measurement. 7 or 8 TVs center of mass energy. And the other is that several of these analyses are really precision measurements, okay? So it took, for some of them, up to 6 years between the end of the run, data taking, and when the first published result was released. Take, for example, W mass by Atlas. So what we can do with these precision QCD, so precise calculations, and for these there have been inclusive and multidifferential cross-section measurements, angular differential up to 3 times differential cross-section. So Atlas released a Z measurement in MLL, rapidity, and cos theta star. Angular coefficients, again from Atlas, ATV analysis, they measured the 8 angular coefficients in Z production. Astonishing result. But you can do also precision electroweak, okay? Probably not the level of LEP, but approaching. So what does it mean? A mixing angle, and again, tau polarization, again, as an handle to access sin theta W. These are only run 1 results. What you can do with W, again, a precision QCD calculation, so precision calculation compared to data, inclusive and differential cross-section, With W, you can be less differential than with Z, clearly. Charge asymmetry and W plus heavy flavor as a constraint to PDFs. Okay. And then the flagship, okay, is the W mass. And we have a slide, I have a slide on this later. But then what can you do also? You can also go a bit further and explore something that maybe a lab has not been yet explored, like the quartic gauge couplings, to a level that lab was not able to access. So we have a lot of diboson, triboson, and electroweak diboson production. That is this QQVV. Okay, so let me first waste a minute on this. So vector boson scattering is something hot in the sense that we had released a lot of new results in the summer. And then you can search for this kind of processes in several finite states. When you have the same sign W bosons, okay, produced in VVS, so the signature is 2 jets, forward, backward jet, and then 2 same sign W bosons. The cross-section is very small for inverse femtobarn, and we had an observation by both Atlas and CMS. Then W plus Z, cross-section is even smaller, and this has been observed by both collaborations. To Z's, this is the cross-section is even smaller than the previous, and for this we only have a hint of an evidence by CMS. The other two, if you want to complete the picture, you should add the same sign W's from photon-photon, so diffractive WW production, and the production of Z plus a photon in VBS. And these are actually, we have results only for run 1. Okay, for example, the diffractive WW places the most stringent constraints on anomalous quartic photon-photon WW vertices, but that need very clean data samples with low pile-up, because you need to find precisely, I mean, to disentangle this process very precisely. So there is no such result updated in run 2. Why are these so important? Because, for example, okay, because they can probe anomalous gauge couplings, and some of them can also be recast in searches for high mass Higgs bosons, like WZ can be recast as a charged Higgs boson produced in VBS and decaying to WZ. This is a summary plot by Atlas. Similar has been produced by CMS, showing all the triboson and electroweak diboson searches compared to the expectation. The expectation is the gray band here, okay, and this is what has been measured in units of the prediction. I think one of the key points from this plot, okay, without even discussing about, so overall there is a good agreement, okay. The key point is that almost all of these measurements are still statistically limited. Okay, the shaded error is the statistical only, and the full error band is the total uncertainty. So that means that there is a high space for improvement. In particular, moving from the run 3 to the ILUMI, so this is a physics case for the ILUMI project, for the ILUMI program, okay? This is a projection from Atlas, a search for same sign WW. This is the limit one can place on the coefficient of one of these operator, this dimension 4 operator, sorry, dimension 6 operator, okay, and moving from the end of run 3 to the ILUMI, one can gain up to a factor of 3, okay, which is what one expects by statistics. And then coming to the flagships of precision electroweak measurements, okay, sin theta and MW. So the effective electron mixing angle, okay, has been measured by both Atlas and CMS, and the way you measure it at colliders is through asymmetry, forward-backward asymmetry in ZLL events. For this, we have only the 8 dV results, and this was the outcome. Okay, essentially, CMS managed to measure it with an uncertainty of 52 parts, 10 to the minus 5, Atlas 36, and these numbers have to be compared to what was done at LEP, at LEP and SLD, which had an error of 16, and to the electroweak precision fit, which is 16, 6 times 10 to the minus 5, okay? So we are still far from both LEP, SLD combined result and electroweak precision observer. Yet it's something that is progressing, okay? How you can measure the mixing angle? Okay, the mixing angle is, it affects the asymmetry, okay, as well known. The symmetry is already, to start with, the Z pole is already small, it's 0.1 for the leptonic one. And then the Z mixes with the photon, and it becomes, and then the asymmetry becomes zero, a bit on the left of the Z peak. And then it has this strong MLL dependence, okay? So this is something one exploits at our colliders, that one studies differentially the asymmetry in the mass. But this is the ideal picture. So this would be the case, this is obtained assuming that one knows the quark direction. Okay, if one knows the quark direction, then defines the forward-backward with respect to the quark direction. But the proto-collision, this is not the case, this is well known. Then there is a dilution factor, so essentially are PDFs, that dilute this ideal picture, and what one observes in the experiment is this picture, okay? So these are the same, is a symmetry as a function of the MLL, but in beams of rapidity of MLL. So at a rapidity 0, everything is symmetric by construction, because the beams are symmetric. You cannot measure any forward-backward asymmetry. And then when you move much farther, okay, in eta, at the edges of your detector, then you start to see, you start to obtain the ideal picture. So this also gives you a hint that the large sensitivity, experimental sensitivity, comes from the high rapidity beams, which are the difficult ones because the experiment at some point has to stop, okay? So the limiting factor at hadron colliders is the PDF uncertainty. So your uncertainty in prescribing what is the fraction of U, D, or S quarks that are contributing to the ZLL production. So if you take the CMS measurements, broken down into systematic and statistics component, you find that what comes out of your current understanding of PDFs, so take your NNN PDF replica 3.0, you get 57 10 to the minus 5, compared to statistical uncertainty, which is almost factor of 2 smaller. However, there is a caveat, because the PDF affect your observable, so your forward-backward asymmetry, in a different way compared to what sin theta W does. Therefore, in principle, they can be disentangled, okay? That's what is shown in this picture. So this is the CMS measurement. This is what comes out of the fit. So if you were to fit this plot with different ansatz on sin theta W, you would get a point. And each point corresponds to a different choice of PDF replica. Okay, so statistically wise, each PDF replica is equivalent, so you have to include all of them and treat them in a statistical sense, as if they were instances of random variables. And one sees that not all of them give the same quality of the fit. Okay, there are some replicas that are produce really bad fits, and one can use this as an extra constraint, saying that the value obtained, for example, in the point in the marker above, has to be weighted down by some factor that is related to the chi-square of the fit. This is called Bayesian reweighting. Said like this is a bit seems a bit fuzzy, but if you think in a more frequentist point of view, then this is equivalent in inputting in your fit not replicas but eigenvectors of PDFs and profiling them. So treat them as nuisance parameters for which you extract your best fit values. So in the high statistic limit, this is equivalent, has been proved, and indeed Atlas uses directly this approach. But this shows you that if you do this, your in situ constraint of the PDFs, okay, the uncertainty gets shrunk by a factor of 2 in the PDFs. This is the result. The CMS one is on the top, an uncertainty of 53. As I said before, Atlas is here, is smaller, 36. The reason, so first of all, the results is the uncertainty has reached the Tevatron level. The reason why Atlas is much better than CMS is essentially because they included in their analysis very forward electrons, okay, with rapidity between 2.5 and 4.9, whereas CMS has to stop here because then there is no more tracker. But for electrons, you can just use the calorimeter. Okay, that's what Atlas managed to do. And the inclusion of these forward electrons, okay, give you a boost in statistics. and a bit also in PDFs, because at high rapidity, you feel less these PDF effects. Okay. Now, if you want to think in the future, what will happen, because of this mechanism that you can in situ constrain the PDFs, you have also some luminosity scaling, okay? Even assuming that, first of all, the PDFs will improve. So this picture is probably not fair, but if the PDFs have to remain as they are, still you could have some luminosity scaling. And the CMS projection to the full Illumi dataset is the red one, is the red line. If you could add the electrons, a bit further electrons, you would have the dashed one, okay? And you see that at most, okay, you will reach something comparable to LEP SLD. Second flagship is the WMAS, okay? So here the challenge is to reach the Electroweak fit accuracy, which is 7, 8, or 6 MeV, depending on who does the fit. Now, the way you measure it at hadron colliders is you compare the data, okay, some sensitive variables in data to templates in Monte Carlo. And the sensitive variables are the lepton transverse momentum, transverse mass, or missing energy. Because of missing energy and transverse mass, there is a preference for clean data sample. So that's why Atlas used 7TV data. The problem, the flow in the construction is that none of these variables are Lorentz invariant, okay? So their sampling distribution does depend on the velocity of the W boson. So unless you know you have a model for W production, you cannot extract the W mass. So the problem is the model uncertainty, the uncertainty coming from both the longitudinal degrees of freedom, so PDFs, and the transverse one. So how perturbative QCD predicts the transverse momentum of the W boson. The take-home message, okay, that I heard once in a talk is that 1% uncertainty on the QT spectrum yields 10 MeV uncertainty on MW. So that gauges, okay, how well you need to know this precision physics. So the approach followed by colliders, Atlas and the Tevatron, was to calibrate W production using Z data. So Z data is a clean sample, you measure it from data, then with limited input prior, you predict what would be the W transverse momentum. But for this, you have to assume some correlation between neutral current and charged current. And okay, I'll say a bit more in a few moments. So this was the result from Atlas, with the measurement with all the fully broken down in all the components. Two things to bring home. First is that the Atlas measurement alone, okay, already competes with the Tevatron combination. Tevatron combination 16 MeV, Atlas claims 19 MeV, and that the measurement is already dominated by systematic uncertainty. Total systematic uncertainty is 19 MeV, and from statistics you have only 7. Second point is about this correlation scheme that you have to assume between the scales, renormalization, factorization scales, is a tricky business. To give you the scale, okay, if that is taken from the Atlas paper, if you were to take the factorization scale as correlated between all quark flavors, but uncorrelated between W and Z production, okay, then the uncertainty on MW would be 30 MeV instead of 8 MeV. So this gives you a scale of how well you have your theory prior has to be. Clearly, there are good reasons to assume that in part the scales must be correlated, but scales are not as statistically well defined as a PDF replica. Okay. So what's the way forward? On one side, improved theoretical calculation. State of the art is something that we don't have as a generator, cannot generate events, and is NLOPS plus NNLL, and full NLO correction, Electroweak and QCD. There are several tools, but not all of them give the same accuracy and the same, okay, I have to speed up. Then you can also think about devising new observables to make your extrapolation more solid, or make new measurements. For example, this is the CMS approach that is pursuing, that you think about ancillary measurements that you improve your knowledge of PDFs, of transverse or WQT, for example. Okay, top quark physics, a lot of new results. Let me just give you some highlight from this summer. Observation of single top plus Z and single top plus gamma by both Atlas and CMS, T plus Z, and single T plus plus photon by CMS. This is also important because you can produce this if there were flavor changing neutral currents between the top and another quark. And this was the object of searches. So you can search for this process which in the CMS, in the standard model doesn't exist or is very suppressed to the level of 10 to the minus 15, 10 to the minus 10. And you may search for these processes either as anomalous single top production. So you produce a lot of single top plus a photon or a Z, because you have up quark in the proton, which radiate the top and a gauge boson, or searching in top decays. So you have two tops, one is a usual decay and the other decays in this way. Projection for dilumi by CMS in branching ratio top to quark gamma and top quark Z. You may reach at most a few 10 to the minus 5, but this is hard to achieve in BSM models. And for the Higgs and top and flavor changing neutral currents with Higgs bosons, these are the projection for dilumi by Atlas. Top mass, another controversial topic. Both CMS and Atlas alone have reached 500 MeV precision, but these numbers have not yet, these measurements have not yet been included in the grand combination. There is still a latency of 4 years between the world average and what the experiments have released. There are various methods to measure it. At the moment, the precision is limited by known experimental effects and known theoretical problems. Okay. What we could achieve in the dilumi run, there is a projection by CMS. This is the full data sample, the 3-atom data sample. The different lines correspond to different ways of extracting W mass, the top mass. The baseline one, so lepton plus jet, is solid black, and the other corresponds to methods that have been proposed in the past years, like measuring it out of cross-section, TT-bar cross-section, gypsy method, single top. The claim by CMS is that you may arrive at this accuracy, okay, of 170 MeV, if you were able to constrain several of that systematics with data, like branching ratio of B quark to leptons, color reconnection, and things like this. Okay, this is the last topic, Higgs boson physics. An overview, a lot of new results, new combination at 13 TeV, including up to 80 femtobarn, an improved coupling fit, new mass measurement, and a new measurement of the width and invisible branching ratio. Differential measurements, I will not talk more about this, but differential measurements in PT Higgs, rapidity, number of jet, PT jet have been remeasured. Okay. Fiducial and fiducial cross-section. Now the highlights are new channels that have been established recently, TTH, VH as a production channel, in particular X2 BB bar. And then the quest for the rare processes X2 mu mu and double X production is continuing. So VH, this was announced in the summer. Okay, the VH with Higgs going to BB bar. This is a typical candidate event recorded by CMS. You have two B jets, so they feature displaced tracks, and two electrons coming from the vertex. In this candidate event, you then have the Z going to a tau, lepton, tau going to hadrons, and tau going to electrons. Sorry, no, this is Z2E. Is the next one that is like this. Okay? This is important because it's the primary mode to constrain the Higgs coupling to B quarks, and is known as challenging. And Tevatron finished its life, CDF finished its life by advertising the evidence of Higgs BB bar, and this is the observation. That's the observation by both Atlas and CMS. They have a simplified analysis in which they show the BB bar mass spectrum, and the signal, the VH signal is in red and is clearly separated from either the gray one, which is the diboson production, standard model diboson, and the background, which is subtracted in these plots. And the mu values are pretty much consistent with the standard model. Okay? So an uncertainty of 0.2 means 5 sigma. Not yet, because it's 0.22. Okay? So if you need to add some other channels, like TTH, H2B bar, and then you exceed this famous 5 sigma number. TTH, so this was the event display with 2000, sorry. So TTH is another candidate event by CMS. Complicated, very complicated final state. It's important because it's the 3-level coupling to the top quark. This is the summary, the individual analysis by Atlas and the individual channels by CMS and the combination. The significance by Atlas is in excess of 6 sigma, because they reloaded the H gamma gamma to 80 femtobarn, okay, and this is also shown. This is the only point where the statistical error is sizable. All the other measurements tend to be systematically dominated already. Coupling fit, then you feed everything into a big fit. This is the outcome. Everything is pretty much standard model-like. We now have a 10% uncertainty on gluon fusion, which is getting closer to the theoretical limit. If you want to look at things that in a more model independent way, you can make ratios of coupling, and that's what Atlas measured. And again, this is pretty much consistent with the standard model. Higgs mass, new analysis by both Atlas and CMS. CMS alone, with just 4 lepton, reaches an accuracy better than a combination Atlas-CMS run 1. New measurement of the width. Sorry that I have to go a bit faster, but my time is over. We have a new measurement of the Higgs of the width from off-shell production, and in this case, it's fine. You can see that the limit from run 1 has already improved by a factor of 2. The observed remain the same, but okay, one cannot say much about this. And finally, we have a new, this is the first time that the invisible Higgs search is combined in the global fit. Okay, it was not the case for run 1. If you do this, you can also lift the degeneracy between a decay to an observable particle, so something that may be very soft that you cannot trigger on, and invisible decays, so really Higgs going to nothing. A candidate event, and the limit set by CMS on the branching ratio X to invisible of 0.24. And this is already better than what was obtained from run 1 using a constrained fit, so where you assume something on kappa V. X to mu mu, both CMS and Atlas are at the 1 sigma level, so if you make your extrapolation, you may expect, you definitely expect evidence by the end of run 3, but we may do even a better job and have something by the end of run 2, so next year, let's say. And then the big dream, okay, double X production. This is a reload of the searches with 30 inverse femtobarn, CMS and Atlas. A combined CMS result gives you a limit around 13 times the standard model expected. Atlas best measurement 15, so we are still far. But if you do your job, your extrapolation, you may conceive to have an evidence per experiment by the end of the ILUMI era. Okay, that's my conclusion. So there has been a rich research program conducted at LHC, precision measurements, understanding of the Higgs sector is in constant improvement. Only fraction run 2 has been exploited so far, okay? And clearly there is more to come with run 3 and ILUMI. Now, several projections to the ILUMI show this appealing potential. I hope to give you, I gave you the idea that there are several measurements that are still statistically limited. That's where the ILUMI project will buy as a lot. And then one may always hope that the precision may be now the path to discoveries, rather than finding new quanta. Okay, that's it. Thank you.
Time for questions. Wait. Otherwise you don't get recorded.
Okay, at the very beginning of the talk, you talked about vector boson scattering. And you didn't say anything about how these events are extracted from backgrounds like PP bar going to 2 vector bosons plus 2 jets in the central region. Could you just say a few words about that? There were
Yes.
some plots, but they were very difficult to read.
I mean, the typical strategy is that you build some, either you look at the variables like the dijet mass or delta y between the 2 jets, and then you assume some Monte Carlo to extrapolate from sidebands, so low values for these variables to the signal region. And then you subtract this from the data and you call this your signal.
Yeah. So at the very beginning, you had some plots with signal and background. This is way early in the talk. Yeah.
Yes.
It's like this. In the top plot, could you tell me what the color code is?
So the signal is the yellow. WZ, so the standard diboson production with extra jets is in red. Non-prompt is blue. So non-prompt means one lepton is true and the other is a fake.
Okay.
And that's it. The others are negligible.
I see. So this is a selection on 2 very forward jets for a large mass.
Yes, yes, yes.
And then
And same sign leptons.
yes, that's important to remove the top.
Yes, yes.
And I see. And then it's very clean at these extremely high mass.
Yes.
Very cool. Thank you very much.
You're welcome.
Any more questions?
On page 17, you were showing the extrapolation. I think it was 17, right? So for the high luminosity LHC detector, CMS also will have, I mean, both detectors will have very high eta tracking. So in principle, your extrapolation should also include forward electrons in this case, or do you think it should not work?
If
This
you,
only goes to 2.8.
if you could, why it was 2.8 and not larger than this?
Right. No, for electrons. But for
so
for electrons.
no.
For electrons, yes.
For high lumen, tracking goes up to 4 for both the detectors. But this is done with reconstructed muons.
Ah, okay. This.
Yes, yes.
That's how the plot is made.
Okay.
If we manage to use it up to 4 out for now, this is
Yes, now electrons is something that is going on now.
this is already extended from 2.4 to 2.8 compared to 1.
Okay, I think we can close here and thank Lorenzo again. We come back at 11:30 for the next talk. Piacere.